Hello everyone, my name is Ting. Today I'm going to show studying from the Journal of Physical Chemistry Letters. It's published as a 2022 years. Its title is The Defect Interseated Cascading Energy Transfer and the Underlying Charge Transfer in European Doping Cesium-Lead Triple Chloride Nanocrystal. In this report, we want to know the energy transfer and the charge transfer mechanisms between the perovskite nanocrystal and the europium ion. So first I want to introduce the perovskite nanocrystal. Perovskite is a crystal of the chemistry formula of the AbS3. The A side usually a organic or inorganic cation, and the B side is the metal ion like the lead or tin, and the S side is the halide like the bromine or iodine. In this report, we will use the cesium-lead triple chloride to make the perovskite nanocrystal. Perovskite nanocrystal have emerged as one of the most exciting materials in recent years, thanks to their exceptional light absorption and the electronic properties. One of the first advantages is the turnable band gap. We can just change the chemical composition. We can get the different band gap of the perovskite nanocrystal, and the second is the high photoluminescence quantum yacht. This means they can emit light very efficiently. So by this advantage, they have some of application. One is the solar cell, and second is the photocatalysis, and then is the light emitting diode we call the LED. And then why we doping the europium ion into the perovskite nanocrystal in this report? First, know that the europium ion is one of the rare earths. It have a unique electron configuration because it have a 4f orbital. Like this, we can see the europium ion. And this makes them have a luminescence from the intra 4f electronic transition, make them have a broader emission wavelength range. So they have a intra transition is make the new relation pathway for the perovskite. So we see this picture by the left. When we excitation the perovskite nanocrystal, the perovskite nanocrystal may do the energy transfer or charge transfer to the europium ion. So make the europium ion can make the intra transition, so we can get the different luminescence. It's not happen in the perovskite nanocrystals. So doping the europium ions created a new relation pathways. And why we choose the europium ion is that they have a similar ionic radius of the lead. The lead is 119 and the europium ion is 108. So this match ionic radius result in lower strength in the perovskite lattice, make the perovskite nanocrystal more stable. In this report, we want to know the energy transfer between the perovskite nanocrystal and the europium ions. So we will use the fluorescence spectroscopy and the transient absorption spectroscopy to know the mechanisms between these two systems. And we synthesize our perovskite nanocrystal by hot injection. Both undoping and the doping perovskite nanocrystal are synthesized through a similar method. We first prepare the cesium OLED as the cesium source. Then The PB precursor we use the lead dipole chloride. And we need to doping the European, so we make the European precursor is this. We adapt the European dipole chloride to make the doping European perovskite nanocrystal. So we injection these two in the bottom and then at high temperature and then struck 30 seconds, then go to the reactor cooling. So we can get the nanocrystal and then we do the purification by centrifugation and the precipitate is dissolved in the tureen. This means allow us to control the doping perovskite nanocrystal have the same crystal structure with the undoping perovskite nanocrystal. So then we will talk about the result. First is the steady state spectra. The yellow line is the cesium lead triple chloride, and the red line is doping European cesium lead triple chloride nanocrystal. First is this picture. The left picture is the absorption spectra. We can see when we doping the European ion, we have some red shapes of the band gap. In the yellow line, its peak is at 398 nanometer, and the red line is at 403 nanometer. So have some red shapes is due to the alteration of the electronic structure of the perovskite. And then we see this small picture, the highlight blue box. We can see when doping the European ion, we have a broader absorption at a longer wavelength is attributed to defect introduction. We can see this broader absorption. And then we see this picture in the right is the photoluminescence spectra. So in absorption have a red shape, also have the red shape in the photoluminescence. The yellow line, the emission peak is at 403 nanometer, and the red line is at 406 nanometers. And we see the red line have some additional immersion. First is that this 1500 nanometer have broadened immersion like this. And then we see this picture, we have few additional immersion peak. One is 592 nanometer and 616 nanometer and 700 nanometer. These three immersion peak is from the intra-transition of European ion. And these three intra-transition immersion is by different type transition. The 592 nanometer is the magnetic dipole transition, and the remaining two, 616 and 700 nanometer, both are the electron dipole transition transition. So the next page we will see that the different wavelengths have a different dynamic, and what the different two types transition have some different dynamic. So this page is the photoluminescence decay trace. First, we see the left picture. We can see the red line have the shorter lifetime in this picture, and the red line is the band gap from the doping European iron perovskite. Why he have the shorter lifetime? We suggest because he have the energy transfer with the European iron. Because we can see this the yellow line. This yellow line is the immersion peak at the 468 nanometer. We say this is a broader immersion peak at the previous page. This immersion peak. So this yellow line have a longer lifetime than the red line, but also have a shorter lifetime than the red line. The red line is from the cesium lead triple chloride perovskite band gap. And why when we doping the European iron in the perovskite, we have a shorter lifetime? Because we suggest it carrier release from the band edge to the defect state before he transition to the European ion. So this shorter is because they do the energy transfer, and so their carrier density becomes lower, and their transfer to the European ion. So he have a shorter lifetime. And then we see this picture at the right. This is the different wavelength immersion peak by the intra-transition of the European ion. And we can see the green line have a very faster decay in the shorter time. The green line is from the 592 nanometer, and we call this the magnetic dipole transition. We call MD transition. And the red line and the yellow line is from the ED transition, electron dipole transition. We call ED transition. So these two types transition have two different dynamic. We can see like this. But we didn't know what happened in this shorter time scale because this time resolute photoluminescence, his time resolution is 200 picoseconds, so we cannot see what happened in the earlier time. So we need to use the femtosecond fluorescence up conversation to know what happened in the earlier time scale. Before we see the results in this page, I will introduce the femtosecond fluorescence up conversation to know. In this, we were using the nonlinear optical process. By this setup, we use the some frequency generation to do the nonlinear optical process, converting lower energy photons into the high energy photons. And in this setup, we can see we used the one pump laser to excitation the sample, and we make the sample have the fluorescence signal. And then we need the other laser pulse. So we make these two signals, the fluorescence and the laser pulse, focus on the nonlinear optical crystal at the same time. Although the frequency mixing, we will get the new signal is up conversation signal, and we use this signal to get the dynamic of the fluorescence. So how do we get the dynamic? We can see this temporal profile. At the time level, we use the laser pulse to excitation the sample, and we can get the fluorescence signal. And then we change the delay time between the laser pulse and the fluorescence. So we can capture the fluorescence dynamic on shorter time scale and the different time scale. So this is the result of the fluorescence up compensation decay trace. In this picture, in the left is the doping European perovskite nanocrystal at the different wavelength, the decay trace. So we can see in this table is the time constant of the European doping perovskite nanocrystal. 440 nanometer is the bandgap immersion peak, and the 468 nanometer is from the defect state immersion peak, and the 592 nanometer is the MD transition, and the 616 nanometer is the ED transition. So we can see their time constant. So we see the red and the blue and the green. We see first is the red. We see the bandgap decay is matched with the defect state growth. This match and the blue, these two, this defect state decay is matched with the MD transition growth, and this decay is matched with this ED transition growth. So by this time constant, we can see they have a cascading energy transfer between the perovskite nanocrystal and the europium ion. So by this, we make the energy transfer pathway like this. The Keller relation pathway is first at the bandgap and then go to the defect state and go to the europium ion to do the intra-transition. So we can see the ND and the ED transition immersion peak. So like this picture, first the bandgap and then the defect, and then go to the europium ion, do the energy transfer. And in the europium ion, it have a cross relation. So by this decay trace, we have that the energy transfer from the cesium-lead triple chloride nanocrystal to europium ion occurs through defect-mediated energy transfer. So next, we know they have the energy transfer from the perovskite to europium ion, but not sure this part is the energy transfer or charge transfer. So next page we will use the transient absorption spectroscopy to study is the energy transfer or charge transfer. So I would first introduce the transition absorption spectroscopy. In this technology, we have the two lights. One is the pump pulse, and the pump is to exciting the sample. This pump is to exciting a sample to the ground state to the exciting state, and the probe is the continuous white line. We use this probe to measure the change in absorption at the various time delay. So we have a different time delay to know the different time, the change, the absorption. And in the transition absorption spectroscopy, the absorption is relative intensity. It's not the absolute intensity, because we make the pump-on absorbance minus the pump-off absorbance. And in this spectroscopy, we will have the two signals. One is the PIB photo-induced radiation and the PIA photo-induced absorption. The photo-induced radiation PIB is the signal from ground state to the excited state, and it also always is the negative absorption. And the PIA is the positive absorption. Is because it's the excited state to the another excited state. It's a new absorption we will not see in the steady state absorption. So this page is the transient absorption spectra by two systems. This picture is from the cesium-lead triple chloride, and this figure B is from the doping europium cesium-lead triple chloride nanocrystal. And we can see they have the identical spectral characteristics, but they have some major changes. One, we can see this PIB signal. In these two systems, the PIB signal recovery rate is different. In the doping plus nanocrystal, his recovery rate is faster. We can see in the same time, the PIB signal at the doping plus nanocrystal is at this. So we can see he have a faster recovery rate. And the second is the PIB signal at the European doping plus nanocrystal have a narrow PIB. And by these two reasons, we can say that it have a charge transfer between the plus nanocrystal and the europium ion, because the carrier density in the europium ion is reduced after we doping the europium ions. And then we have a new negative reaction. It's from the 412 nanometer to 430 nanometer. We can see it happened in the doping plus nanocrystal, but we will not see in the undoping plus nanocrystal. And this, we say this is from either a formation of an intermediate charge transfer or the presence of the defect state. But this absorption we will not see in the steady state absorption spectra. So we say this is by the charge transfer, and is past the defect to do the charge transfer. So by the fluorescence spectroscopy and the transient absorption spectroscopy, we have the conclusion One is the cross-relation process at the European state. The MD translation is faster than the ED translation. And the second is, by this report, we have the new insight into the doping European Pascal nanocrystal, the energy transfer and the charge transfer mechanisms. And layer mechanisms by this picture we can see. They have the charge transfer to the defect and do the energy transfer to the European ion and make the cross relation. So today, this is my report. Thank you.